Hey guys, so today our focus is specifically on enzymes since that's kind of where we left off. We were talking about metabolism and we left off talking about how sugar would happen spontaneously, but it would be so slow that life could not exist. And what makes that possible is enzymes. So I will share my screen and find the right PowerPoint. Should be this one right here. And get it presenting. Okay, come on. So our focus today is just on enzymes. And understand that enzymes are macromolecules that catalyze or speed up reactions by lowering the activation energy. So what we were saying with that sucrose, with it taking 1,000 years for this reaction to happen spontaneously, well, obviously that means that the activation energy is so high that it takes all this time. By adding in the enzyme, we lower the activation energy and make it start sooner, make it start easier. So it's not taking 1,000 years. So it's that activation energy that's basically determining how long it takes for it to start and happen spontaneously. Enzymes are not consumed by the reaction, so they're used over and over and over. Once they have finished with the reaction, they'll be released and they'll go back and do the whole process over again with another glucose molecule or whatever it is that they're reacting with. Enzymes are a type of protein. So that means that they follow those rules with proteins. And what is the key thing that we always remember when we're talking about proteins? Shape determines function. If you change the shape, you change the function. Okay. So enzymes also typically end in ASE, catalase, sucrase, protease, lipase. And a lot of times they'll tell you kind of what they're working on with that ASE as well. Okay, so an enzyme acts on a reactant called a substrate. So the substrate is the reactant. It's the thing that we're starting with. The active site is the area for the substrate to bind. And so you'll notice on this little enzyme, we've got these really specific shapes. Something that doesn't fit those shapes won't work with that enzyme. So the active site here is open, and here are our substrates, and you can kind of see how they should fit. So the substrates will be held in the active sites by kind of a weak interaction. Remember, this is not a permanent change. This is something that we're doing to get them close enough to function. Okay. So we call this the enzyme substrate complex. Once they've reached this point, we're going to adjust the activation energy, right? Because the idea is we're lowering the activation energy, so it's more likely to do the reaction more quickly. So ultimately, the substrates will be converted into the products. So here you see that we have definitely had a change. The products will be released and the enzyme is available again to go through the process over and over and over. So the idea is really that while we're talking about it like, oh, this specific thing fits in this slot and nothing else does, the reality is that we have what we call an induced fit. So the enzyme will actually change the shape of the active site to allow the substrate to bind better. So the substrate gets into that area and it triggers the enzyme to shift its shape. So you'll notice that it kind of closes around it a little bit to form that complex. So while we say it fits a certain shape, the reality is that it triggers it to shift its shape a little bit to better fit. So when we're talking about enzyme catabolism, remember catabolism, that's dissecting the cat, where we have the big cat and we divide it into smaller pieces. So enzymes will help break down complex molecules. So here you'll notice our substrate comes in, it fits around it, and it causes it to break into two separate pieces in this specific reaction that's being modeled. In enzyme anabolism, we're taking two separate substrates, and notice once they're both there, it causes the shift in fit, the induced fit. Then the reaction occurs and it will release the product, and notice that the two have become one. Remember, anabolism, we're taking smaller ones and we're bringing them together to form one larger one. So that's going to help build complex molecules using our enzymes for anabolism. So then that takes us to the idea of the effects on enzymes. So we know that enzymes are proteins, which means that their three-dimensional shape can be affected by different factors. And if we change the shape, we change the function. So they may not work correctly if we change their shape. So the efficiency of enzymes can be affected by temperature, by pH, by other chemicals. Remember, a change in shape means a change in function. So we have what we call optimal conditions for our different enzymes. This is the best temperature, the best pH that allows the enzyme to function optimally at their best. We're always going to have the highest rate of reaction in these optimal conditions. Will it still work outside of the optimal conditions? Yes, to a certain point, and then you're going to reach a point where it just simply will not work at all. But you will see a decline outside of the optimal conditions. So the rate of enzyme activity increases with temperature due to collisions up to a certain point. And then once it goes beyond that specific point, the enzyme will begin to denature, begin to change its shape, therefore no longer functioning properly. Enzymes function best at a specific pH. Outside of that normal pH range can cause hydrogen bonds in the enzyme to break, changing the shape of the enzyme, therefore causing it to denature, changing and reducing its functionality. So here you'll notice we have three different enzymes, and the three different enzymes have three different optimal temperature ranges. Enzyme 1 does best about 20. Enzyme 2 does best about, I'd say, maybe 55-ish. And enzyme 3, I'd say it's probably somewhere around 85, 87, something like that. But you see, those are their optimal range. But you'll also notice that they're still having reactions away from that optimal range. They're just not as good. They're not going to have as good a rate of reaction. Additionally, we may have cofactors that will be involved. Cofactors are going to be non-protein molecules. A lot of times these may be our vitamins or minerals, and they're going to assist the enzyme function. Typically, we've got inorganic cofactors like metals, some of our minerals. They can be bound either loosely or tightly. Sometimes we have what we call a holoenzyme. That's an enzyme with the cofactor actually attached to it. So the cofactor has to be attached physically to the enzyme to make it work. We also have coenzymes that are organic factors. So cofactors are the non-protein like inorganics. And then we have our organic cofactors. Those are coenzymes like our vitamins. So cofactors are inorganic, coenzymes organic. Then there are enzyme inhibitors. These are molecules that reduce the activity of a specific enzyme. So we can actually block and even though it may be at its optimal conditions, we can actually still reduce the reactivity of that enzyme with enzyme inhibitors. Inhibition can be permanent, so it basically makes that enzyme totally useless, or it can be reversible, so we can temporarily make the enzyme not work, and then later we can reverse that and it'll be functional again. Permanent inhibitors will actually bind with covalent bonds. And remember, covalent bonds are actually very strong and they're a lot harder to break. Toxins and poisons would often be our permanent inhibitors because the body doesn't naturally want to just totally disable its enzymes in most cases. Reversible inhibitors are going to bind with weak interactions, for example, hydrogen bonds, things like that. So here you see we have a substrate fitting to its active site. That's a normal substrate. Competitive inhibitors reduce the enzyme activity by blocking substrates from binding to the active site. So notice how perfectly our substrate fits our active site. If you look at our second enzyme, you'll notice that it has changed its shape somewhat, and so it's no longer the perfect fit for the substrate. Inhibition can be reversed with increased substrate concentrations. So a competitive inhibitor, notice here we've put a molecule in that's blocking part of the active site, and if that's blocked, the other one cannot fit properly. So it bounces off and bounces off. Here we've got our substrate and active site again, and we have what we call a non-competitive inhibition. Non-competitive inhibitors are going to bind to an area other than the active site. We call that an allosteric site. That will change the shape of the active site, preventing substrates from binding. So I don't know if you've noticed that there's this little box down here at the bottom. Well, this is a type of allosteric inhibition where the non-competitive inhibitor comes in and it attaches to this allosteric site, which caused the enzyme shape to change. And now, once again, that substrate simply will not fit. It's going to bounce off. We're not going to have that change in rate of reaction because the enzyme's not working. So hopefully that gives you a little better idea of enzymes, what they do and how they function, and how we can stop them from functioning. Okay, so I'm going to stop sharing, and I'll see you for the next episode.